In this lecture, we will study application of beats. First, a quick review about the phenomena of beats. Beats are produced by waves which are periodic, simple harmonic in nature, and these are fast oscillations, meaning that the angular frequency is large. The component waves should be collinear and they should have slightly different frequencies. And the difference is less than 10 Hz. Upon superposition, the resultant amplitude varies slowly. With time, there is a rise and fall in sound, and this rise and fall in sound is referred to as beats. Also, the resultant motion is not simple harmonic in nature, because the amplitude varies. The fast oscillations are modulated, they are averaged out, and this modulation of sound is called beats. So amplitude modulation occurs, and this amplitude modulation is called beats. So if the resultant wave is along y-axis and this is the time axis, then so this is maxima, minima, and so on. So these are maxima, and these are minima, and this is one beat, this is the following beat, and it goes on like that. And the beat frequency, which is number of beats per second, let us denote by delta f, is the difference between the component linear frequencies, and obviously this is small compared to the individual frequencies, that is the fast oscillations. We now move on to the application. We will discuss in this lecture tuning of a guitar. Guitar is a plucked string instrument that is played with a pick or fingers. If your guitar is not tuned correctly, it will not produce the desired sound, no matter how well you play on it. So, tuning a guitar is the first step that one undertakes as a rule. So, why the necessity of tuning? Why tuning? Or what is the need of tuning? This is to produce desired, clear and stable sound or note from strings of the guitar, and not noise. We come to the principle of tuning a guitar. So the principle of tuning a guitar is that, number one, tighter string means its frequency is large, or frequency increases upon tightening, and on loosening or slackening, means frequency decreases. So all this depends upon this formula. So frequency is proportional to under root the tension, which is associated with how much tight or slacken a guitar string is. And number two is the number of beats heard, which is the difference of the two component frequencies. Suppose F1 is greater than F2, F1 and F2 being frequency of two strings. Now if more beats are heard, that is if delta F is large, then what we should do is we should reduce the frequency F1, which is the larger of the two, and increase the lower frequency, that is increase F2, the lower of the two, say. And this is done by tightening the string so that F2 goes up, and slackening or loosening a bit this string so that now the difference reduces, and so the number of beats will now come down. Things will be clearer when we take example of two guitar strings, which we do now. A standard guitar has 6 strings. And they vibrate to generate sound. So let us draw the 6 strings. 1, 2, 3, 4, 5, and 6, and the strings are named as E, A, D, G, B, and E again, and the mnemonic to remember this order is elephant and donkey grow big ears. this string is the thickest of all and this string is the thinnest of all. The frequency of these strings are, this has the lowest frequency 82.41 Hz. The frequency of string A is 110 Hz. That of D is 146.83 Hz. That of G is 196 Hz. B has a frequency of 246.94 Hz. And this E has a frequency, the largest one is 329.63 Hz. So this string has lowest pitch or frequency and it is flat so far as the sound emitted is concerned, while this E is of highest pitch or frequency and it emits a sharp sound. The frequencies referred to here are fundamental frequencies. Or the first harmonics. The next part of the discussion will refer always to this diagram or figure. Let us now address the question what we mean by tuning. What is tuning of a guitar? What does it mean? So let us write what is tuning. In guitars. Tuning a guitar actually refers to matching the frequency of each string with the fundamental frequencies. So this is what we mean by tuning. And let us illustrate. We note that the strings E, the low E, and A will match in some of their harmonics. For instance, if we multiply it with 4 and if we multiply this with 3, then the answer is 329.64 Hz and this turns out to be 330 Hz. So the difference between these two frequencies is delta F equal to 0.36 per second, and if we multiply it by 3 we get 1.08 per 3 seconds. So in 3 seconds we hear about 1 beat. If A and E are at these frequencies, that is, they are tuned, and if they are not tuned, number of beats will be greater. And this actually means, suppose this is the E string and this is the A string, this is low E, and there are 4 harmonics, so we'll have four humps, and A has 3 harmonics, so it will vibrate in this way. So this is antinode, and these are nodes. So clearly the fourth harmonic of E vibrates in 4 antinodes and 5 nodes, whereas the string A generates third harmonic when it vibrates with 3 antinodes and 4 nodes. And then their frequencies are slightly different so as to produce 1 beat in 3 seconds. We next consider the string A and D, and if we multiply this with 4, that is considered the fourth harmonic, we get 440 Hz because this is 110, and let us multiply this with 3, that is considered the third harmonic, that gives so that again we find that they are very close to each other. They are slightly different in frequencies, and the beats they produce will be delta F, and the difference is 0.49 per second, and if we multiply by 2 we get 0.98 per 2 seconds. So when struck simultaneously to generate the third harmonic for D and fourth harmonic for A, number of beats heard in 2 seconds will be 1. To tune D with G, let us consider the fourth harmonic. Let us multiply it by 4, so it turns out to be 587.32 Hz, and we will consider the third harmonic for G, so multiply it with 3 to end up with 588 Hz. So again we find that they are very close to each other, so they will generate beats, and delta F, that is number of beats heard per second, is 0.68 per second, and if we multiply it with 3 we get 2.04 per 3 seconds. So when D is struck in the fourth harmonic and G in the third, the number of beats heard in 3 seconds will be 2. If it is so, we will call they are tuned, but if we hear a larger number of beats, then obviously they are detuned, they are not tuned, and we have to tune them. It is now the turn of the strings B and E to be tuned. Let us consider the third harmonic of E. So multiplying with 3 gives us 247.23 Hz, which is very close to the frequency of B, which is 246.94 Hz. So these two frequencies when struck together will produce beats 0.29 per second, and if we multiply by 4 we end up with 1.16 per 4 seconds. Again, if this low E string is vibrated in the fourth harmonic, we get 329.64 Hz, which is very close to the high E frequency in its fundamental or first harmonic. So we can compare them. And when sounded together, they will produce 0.01 bits in 1 second. If we multiply it by 100, we end up with 1 per 100 seconds. So this is practically 0. So no beats will be heard if they are properly tuned. That is, if they maintain these frequencies. Let us now mention how tuning is actually done. So the strings that are tuned will place in the first column, that is, these strings will be sounded together. and number of bits heard that we'll place in this column, and this is the formula assuming that F1 is larger than F2. And finally, what we do is to tighten the string or to loosen the string, and we'll mention here which string is to be tightened and which one is to be loosened. Let us start our experiment by trying to tune the strings E low and A. So the fourth harmonic is generated in E. This E has lower frequency, so we write E low, and the third harmonic of A is sounded together, as a result of which some beats are heard, which suppose is greater than 1 per 3 seconds. And if this is so, then we have to reduce this gap, and this gap reduction is possible in two ways. One is by decreasing the higher frequency. So we have to decrease the frequency of A, and this can be done by loosening it. So A string has to be loosened and the frequency of E, which has the lower frequency, has to be enhanced, and this can be done by tightening it. And if by doing it number of bits reduced to 1.08 per 3 seconds, we say that these two strings are tuned. We now suppose that the string A of the guitar is vibrated in its fourth harmonic and D is vibrated in its third harmonic, so that number of bits that one should hear is nearly 1 in 2 seconds. But suppose we hear more number of bits, that is greater than 1 per 2 seconds, which means this gap has to be reduced. The frequency of A has been fixed earlier, and therefore the option left is to reduce the higher frequency, that is the frequency possessed by D, which can be done if we loosen the string. So D has to be loosened, so that number of bits fall to 1 in 2 seconds. Tuning of G and D can be done by generating the fourth harmonic in D and the third harmonic in G, so that now number of bits heard should be 2 in 3 seconds. And suppose we hear larger number of bits. Suppose they are detuned. G is detuned to D. Now D has already been tuned with respect to A or E. So the task is to adjust the frequency of G, which is the higher of the two, and therefore we have to diminish the frequency of G, and that can be done by loosening it. So we have to loosen this G string. Next, tuning of B and E higher. So here is the fresh diagram. Now suppose the third harmonic in E is generated and simultaneously B is sounded, and therefore we should hear a beat of 1 in 4 seconds. So let us write it down. So now E low is sounded in the third harmonic and B is sounded in its fundamental, and if 1.16 beats are heard in 4 seconds, then they are tuned. But suppose they are not tuned and larger number of beats are heard, and then this gap can be reduced. We will not touch E low because this has already been tuned or set at fundamental. So let us adjust B. Now in this case B has lower frequency, which can be increased by tightening it. So B has to be tightened. And finally we sound E low in its fourth harmonic and high E in its fundamental, and if they are tuned, they should not produce any beats. But if beats are heard, we have to adjust E high, which has slightly lower frequency with respect to this one. So we have to increase it, and that can be done by tightening it. So let us complete the table. Having perfectly tuned the guitar strings, it is now ready to be played on. We here gave an ideal description of tuning a guitar. Reality is, however, different. Depends on, say, type and quality of string. The string may not be new and may be dirty, may contain rust, it may be worn out, and all these factors causes mass per unit length mu to change. If mu, that is mass per unit length, changes, then as per this formula, frequency F changes. And direct quantitative measurement is not possible regarding the amount of change. So the spoil is done, and adjustments are to be made accordingly. And let me conclude by saying that musicians or people in the world of music are far, far better and capable of doing these adjustments than a physicist